Okay, I'm registering now. I'm recording, sorry. All right, we should go on with the notion of isomorphism. But first, I would like to ask everybody, the ones who are in class here and the many who are in remote, do you have any questions about about yesterday's lecture? Above all, can you hear me well?
Yes, we can hear you.
Okay. I received another proof for yesterday's problem, which was not complete, but it's all right. Try like that, and it's a good thing to do. Okay, we'll have some more interesting.
Excuse me, Professor.
Pardon me?
Excuse me. Can you hear me?
I can. Tell me.
And excuse me, I'm a bit doubtful about isomorphism, especially the question you asked yesterday about how to divide them. And I mean, the vertex that we can take isomorphism benefits. I mean.
Okay, I'm going through it today also. It was just the beginning of the subject. So let's go to that in particular. Okay. Um, let's draw a couple of very simple, and not only simple in technical terms, but also
Excuse me,
easy.
can you hear me?
Tell me.
I want to know if I can find the last online session in the virtual website of the university.
You can find it in the program page of my website. Okay.
I can find all the video, all the online sessions.
Everything. You find the link to the recording and the and whatever I draw here. Okay.
So not in the your virtual website, in your page.
Through the virtual web page, you can go to my page, or you can go directly to my page and find everything. Also, recordings of last year's classes. Okay.
Okay, thank you.
Very well. So let's take a couple of easy graphs like this. And so I give names here: capital A, capital B, capital C, capital D, and small a, small b, small c, and small d. And here another one. E, F, G, H, and small e, small f, small g, and small h. Okay, these are two graphs. They are different because they have different vertices, different edges, and so on. So let's try to find some isomorphisms. Okay, so I need theta from vertices to vertices, okay, and theta sends one possible such isomorphism. The easiest that you can find just by translating is send A to E, B to F, C to G, and D to H. And you also have from edges to edges, sending what? Small a to small e, small b to small f, small c to small g, and small d to small h. Okay? And this is a good isomorphism. It is actually an isomorphism. Why? Because if I pick up any edge here, let's say small b, what are the ends of small b? Capital B, capital C. Let's look at the image of small b. The image of small b is small f. What are its ends? Capital F, capital G, and actually capital F is the image of capital B, capital G is the image of capital C. So the condition is satisfied not only for small b and small f, but also for small a and small e, small d and small h, small c and small g. So this is actually an isomorphism between these two graphs. Can anybody find another isomorphism between these two graphs?
The same number of vertices and sides.
Pardon me?
The same number of vertices.
The number?
The number of vertices are same, so
That's not enough.
we can say that
That's absolutely not enough.
the size of the graphs are all same.
That's absolutely not enough. Look, I could have.
Professor, maybe it's because they are not intersecting.
Just a moment. If I take this graph, it has the same number of vertices and the same number of edges of the one before, okay? 4 vertices, 4 edges, but it is not isomorphic. Why? Okay, let's try something like that, okay? Let me do this. This is an interesting thing, okay? So that's a good thing to work on. Okay, so it's true that I can do a theta from a bijection from vertices to vertices. For instance, by sending A to L, B to capital M, capital C to capital N, capital D to capital O, and sending small a to small l, small b to small m, small c to small n, and small d to small o. But it's not an isomorphism. Why? Don't forget, and this is actually the reason why many students fail at their exam, because they don't take care of this. It's exactly, do you remember the silly gag I did yesterday of 2 towns having the same names for squares and for streets? Can you, here we have the same thing. Here is one village, and here is the other village. And you have...
They have the same function that connect the vertices with the edge.
You must have what? What I said before in this case. It's not enough to have bijections. You must have that if you take any any edge here and take its corresponding edge in the other graph, to the ends of this edge, to the two vertices ends of this edge, there must correspond the two vertices which are end of the corresponding edge. Okay, this is not possible in this case. Okay, can we find something which is not working? Here are two bijections, and this is not enough. These are not isomorphic graphs. Why? Let's see what happens. For instance, to small a. Small a has ends a and b. Okay. Small l, which corresponds to small a, has capital L and capital M as ends. Oh, yeah, okay, it's working. Let's go on, because it must work for all edges. Okay, so let's take B. A small b, this edge, has small m in correspondence, okay? What are the ends of small b? Capital B, capital C. What are the ends of small m? Capital M, capital N. Oh, how good. These are exactly what we were expecting. Let's go on. Small c, its ends are capital C and capital D. What is the corresponding edge of small c? Small n. Okay, what are the ends of small n? Capital N, capital O. Capital N, capital O. Sorry, we were with the C, and it's all right because capital N corresponds to capital C, capital O corresponds to capital D. So everything looks fine, but let's see with the last edge, small d, and we go with the small d, we must go to small o. What are the ends of small d? Capital B, capital D. What are the ends of a small o? Capital L, capital O. But unfortunately, they are not the correct ones. Okay? We should have that psi, let's give names to these graphs. X and Y. So psi Y of phi of D is what? The ends of phi of D is of small d is small o. They are L and O. Okay? But if I take psi x of small d, what are the ends of small d here? B and D. Okay? But L is the D is, where is it? D goes to N. So is this theta of B theta of D? No, because theta of B is M and theta of D is O. So only one is correct, okay? But theta of B is not. Okay, so these two graphs are not isomorphic, although they have the same number of edges, same number of vertices. So it is possible to build correspondences between vertices of X and vertices of Y, edges of X and edges of Y, but they do not respect, even for just one vertex, it's enough for saying this is not an isomorphism, okay? They are not virtually, morally the same graph. This is what I mean. And again, let me say that silly thing, if X were the map of one town and Y were the map of another town, you cannot go through this town Y with the map of town X. Is that clear? It should be clear. How can you make it formal? We are in mathematical methods. What's the mathematical method for formalizing this fact that you cannot travel through Y with the map of X? Exactly what has been given in the book and in class. Okay? Not only to have these two bijections, but also that this condition is respected. And here, this condition is not respected. So this is not an isomorphism. Is that clear enough for everybody?
Yes.
Okay. So let's go back here. Where I have given a good isomorphism, you can check that. So I'll do it very quickly without writing. Small a, its ends, capital A, capital B. Phi of small a, small e, what are its ends? Capital E, capital F. Capital E, capital F are exactly theta of capital A, theta of capital B. Small b, its ends, capital B, capital C. Phi of small b, small f. What are the ends of small f? Capital F, capital G. Capital F, capital G are exactly theta of B and theta of C. So it's all right. Small c, what are the ends of small c? Capital C, capital D. What's the corresponding edge here of small c? Small c, it's a small g. What are the ends of small g? Capital G, capital H. But capital G, capital H are exactly theta capital C, theta capital D. So the condition is respected. Small d, what are its ends? Capital B, capital D. What is phi of d, of small d? Phi of small d is small h. What are the ends of small h? Capital F, capital H. But capital F is the theta of capital B, and capital H is theta of capital D. So for all of these edges, the condition is satisfied, and this is a legitimate isomorphism. Now my question, can you find another one? Can you find another isomorphism between these two graphs? Okay, here in the classroom, we have already somebody eager to give me this isomorphism. Anybody from outside suggesting two new bijections? Can't you see that there is some symmetry in all this which allows for a different isomorphism than the one I've just written? Okay, I waited enough time, so please give me yours. capital A to, can you please take, oh, sorry, yes, capital A to capital E, capital B to capital F, okay, and consequently, small a to, yeah,
And small b to small h this time.
B to small h,
And C again to G. And D to F.
and E to F. Yes, it's all right. It's again a legitimate isomorphism because you have that if you check for all of these, you will see that actually the ends of this go to the ends of this, the ends of this to the ends of this, to the ends of this to the ends of this, and the ends of this to the ends of this, okay? So we have in this case two different isomorphisms and no more. It is not possible to find any more isomorphisms between these two. Okay, this is interesting. We are going even to consider isomorphisms of a graph to itself. And this is interesting because you might also consider that these are two images of the same graph, okay? I given for distinguishing them different names to all of them. But actually, we could also have considered this, that I have only this and I can have different, just two isomorphism of the graph to itself, okay? One is always there, and it is called the identity, okay? And it's very natural. A to itself, everything to itself. This is called the identity. And actually, when I have an isomorphism of a graph to itself, it is called an automorphism, meaning a self-isomorphism, okay? Small a to small b to small b, small c to small c, small d to small d. Okay, this is one, and this is called the identity. But the symmetry of a graph is exactly how many is given but by how many automorphisms you can have of that graph to itself. And here we have a very simple symmetry because the only other automorphism beyond the identity, which is always there, is that I send A to itself, I mean capital A to itself, capital B to itself, but capital C to capital D, capital D to capital C, small a to itself, small b to small d, small c to itself, small d to small b. Okay? This is another automorphism. Okay? Question. Try to guess. Oh, look to one thing. If I have, oh, this I can, I have an extra, rimuovere la pagina, sì. Okay, Okay, look, when I have a simple graph, actually a legitimate isomorphism can be just be given by the if the two graphs are actually isomorphic, it is enough to say where the vertices go. If you have two simple graphs and actually an isomorphism exists, it is enough to say where the vertices go, okay? Just to give theta, if there is a legitimate isomorphism. Of course, as in this case, it is absolutely not enough because you don't have any isomorphism in this case. Anyway, for one more case, I'll still give, at least at the beginning, also the correspondences for the edges. But I want you to tell me. Okay, now I'll have only these vertices and these edges, so just not to always say capital and small and capital, I'll give different names to the edges. So E, F, and G. And I will not say small f, capital A, okay? All right, so now, a guess. How many different automorphisms can you have for this graph? What do you think? How many isomorphisms of the graph to itself? The way we had here, okay? So that we had here we had two. One is compulsory, the identity, and here we had another one, okay? Now, how many can we have here? What's your guess? Yours? Sorry? Your guess is 6. Yours?
I think yeah, 6.
Yours?
No, I would say 3, but I think
You would say 3. And I guess I know what you are thinking.
I think it's
You think it is? Sorry?
4.
4?
Yeah.
Oh, interesting that. Okay. The Turkish lady here is right. It is 6. And okay, of course we have identity. So A to A, B to B, and C to C, and G to G, E to E, F to F, okay? And this is compulsory, so no problem. I think that the Italian guy here is thinking of this, A to B, B to C, C to A, and correspondingly G to E, E to F, and F to G, and that the third that he is thinking of is A to C, C to B, B to A, and understandably enough, F to E, E to G, and G to F. Am I right? Okay. But a friend here in the loudspeaker thinks of 4, and I think that I also know what's the fourth he's thinking of. A to A, B to C, C to B. But we, consequently, of course, we have G to F, E to itself, and F to G. Okay, so we have the fourth one, but there are two more in the same way, meaning that now we have flipped along a vertical line, but we can flip along this line and flip along this line. So we can have that A goes to C, that B goes to itself, and C goes to A, and consequently G goes to E, E goes to G, and F goes to itself. And of course, we also have, I can write also here, but we also have that we can send A to B, B to A, C to itself, and consequently G to itself, F to E, and E to F. Okay? And so we have the 6 of them. Not only is it a set of automorphism, it is also a group, but this is beyond what I'm willing to do in this course. It would be anyway very interesting because it is a group under the operation of composition of maps. Okay, so the interesting thing is that if you compose, for instance, one flipping with another, you get a rotation, and if you compose a rotation with a rotation, you get a rotation, and it is a very small but interesting group of symmetries. And so this is very symmetric because it has quite a lot of symmetries, we call them, so the automorphisms, much more than this, which has only 2, okay? Well, this question, or similar to it, was the way I had to reject many students, not being able to find an isomorphism different from this one I had written, okay? To find the other one, okay? This idea of isomorphism is very interesting, not so much for just graph theory, but in general for mathematics. Mathematics is built of objects, structures, and isomorphism between structures. If you missed that when you did your linear algebra course, you have missed the most important part of the course. The important thing is that in linear algebra, you have that many physical situations are linear, are describable by vector spaces, and what is important is that you can emulate one vector space with another, and this is the idea of isomorphism, okay? But that's, again, beyond the goal of this course. I have 2 of these. Okay. So one more page, and now let's go back to, okay. Find an isomorphism between the graphs G and H of examples 1 and 2, different from the one given, if you want, but it's not that important, but it is a good exercise if you have problems with the idea of isomorphism, okay? I'll do this, show that there are 11 non-isomorphic simple graphs on 4 vertices. Why am I going to do it? Because I want you to understand these non-isomorphic simple graphs the tricks which are in this statement, okay? But this is a very, very, very nice exercise. Show that the following graphs are not isomorphic. And again, as I told you, do you remember that for proving that thing of the number of edges which was less than or equal to me, binomial coefficient me over 2, you had to invent the idea of complete graphs, and the complete graph came after in the following section. Again, we have something like this. It will be something which will come in one of the following sections, which can help us to see immediately that these two graphs are not isomorphic. Any idea to start? I want to dedicate, okay, it's already 10 to 5. All right, no more than 10 minutes. Any idea for showing that these two are not isomorphic? Let's think of something. Okay, just for the vertices, and it would not be enough, how many bijections do we have between vertices on the left and vertices on the right? Do you know that? How many possible bijections from this set of vertices to this set of vertices we have? Do you know that?
100.
And how did you come to this 120? Because it is?
Permutation of 5.
Yes, it is a 5 factorial, okay? So it is factorial of 5. So we have, in this case, already quite a lot of possible bijections here. And how many edges do we have? 1, 2, 3, 4, 5, 6, 7, 8. And so, as for bijections of edges on the left, 2 edges on the right, we have a very big number because it is 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 4 times 3 times 2, okay? So I don't know how much it is, but it's quite a big number. So it is true that I could try all of them and see whether one of them respects this the condition we have seen for being we should test each bijection on the vertices with each bijection on the edges, so it becomes a terribly big number. But it's not necessary. Unfortunately, in the last tens of years, many things have been done like this, brute force. Why? Because we have very powerful computers, and so you let the computer do it. But here we have constraints. Do you have any idea? Should we send any vertex here on the left to any vertex here on the right? Or is there a very strong constraint that you can see? I think that there is one particular vertex on the left which has to go to a particular vertex on the right. No idea? No idea from remote? Oh, okay. A particular edge which has to go to a particular edge. If we want to preserve that thing, that if I take the ends of the initial, of the edge here on the left, the ends of the edge on the left must go to the corresponding vertices on the right, okay? So, is there an edge which is in a very particular situation or not? There is a loop. A loop must go to a loop. If there is a loop on the left and the loop on the right, necessarily the one loop we have here must go to the one loop we have here. Why? Because let's give a name to this vertex, A, okay, and the name to this vertex, L. Okay, what are the ends of this edge? A and again A, and you must have that the corresponding edge must have again as ends the same vertex. So it's not possible that you send this edge, for instance, to this edge. Why? Because it's impossible that the ends of this are the corresponding vertices to the ends of this. Why? Because here the ends are the same vertex, and here the ends are two different vertices. So the only possibility for this loop is to go to the loop we have on the right. If we had two loops here and two loops there, we would have more possibilities. But since we have only one loop on the left and only one loop on the right, we are bound to send this loop to this loop, and consequently to send this vertex to this vertex. Okay? So, was it 120? Now, as for the possible interesting bijections from vertices to vertices, it is already much, much less. Why? Because now we have just 4 factorial, which is 24. So from 120, we have gone to 24. But can we do more than that?
Because of the X, maybe
Please, I'm sorry.
because of the X edges, maybe it will the number will balance. Edge bijection, because of edge bijections.
Okay,
Possible?
but in the bijection, is there something else which is a constraint? No idea from outside? Okay, I'll tell you. Look at these multiple edges. These two edges have the same ends. So the corresponding edges on the right must have the same ends. So is it possible to send, say, this edge, can you see what I'm doing? This edge to this edge, and this edge, say, to this edge? No. Why? Because this edge has these two ends, and this edge has another end. So it's not possible that our constraint is satisfied. So what is sure is that since we have only one pair of multiple edges on the left, only one pair of multiple edges on the right, it is sure that these two multiple edges must go to these two multiple edges. And here we could have actually many possibilities, because I could choose to send the inner multiple edge to the inner multiple edge here, or to send it to the outer multiple edge, to send the above vertex to the above vertex, or to send the above vertex to the down vertex, okay? Okay, so this is another constraint, less strong than this very strong constraint. This edge must go to this edge, and so this vertex must go to this vertex. But with this other set of constraints, I can already say that it's not possible. Why? Any idea? Okay, I'll tell you. So these two vertices, the vertices with which are ends of the multiple edges, must go, I don't know in which order, to these two vertices, okay? But look, one of these vertices is adjacent to the one of the loop, okay? And so its corresponding vertex should be adjacent to the one of the loop. And this is not the case. Assume that you send this vertex to this vertex, then it's not possible because this edge would not know where to go because this vertex end of a multiple edge and this vertex end of a loop are ends of the same edge. They are adjacent, we can say. But here, the end of the loop and both ends of the multiple edges are not adjacent. They are not ends of the same edge. So it is not possible because these two constraints should be verified, but it's not possible. So, but another way of saying is look at something which has to be preserved by an isomorphism. If I send a vertex to a vertex, what is surely the same on one and on the other is the number of edges incident to that vertex. So I could, in principle, send this vertex to this vertex. Why? Because there are two edges incident to it. There are two edges incident to it. Okay? So one thing which has to be preserved is this number, the number of edges going to a particular vertex. We'll have a name for that in, I think, the next section, which is the degree of a vertex. The degree of a vertex has to be preserved by an isomorphism. And actually, we have the same degrees, as we shall call them in a few minutes. Here we have 3, and here we have 3. Here we have 4, and here we have 4. Here we have 3, and here we have 3. Here we have 2, here we have 2. And here we'll say that we have 4 because each loop is counted twice when we define this, degree. But what do I have? I have here, for instance, that the only vertex of degree 2 is adjacent to the only vertex of degree 3, but here it's not like that. The only vertex of degree 2 is not adjacent to a vertex of degree 3. It's adjacent to a vertex of degree 4 on one side and degree 4 on the other side. So there is no possible isomorphism between these two graphs. Okay? So you can see how fine is this and delicate is this notion of isomorphism between graphs. Okay? Please do understand in depth this. And if you have problems, tell me. You can write to me. We can fix office hours for discussing that personally. Okay? No problem, we'll have the possibility of meeting through Teams, okay? Now, okay, this requires quite a lot of drawing. 11 non-isomorphic simple graphs on 4 vertices, okay? Here with a small board like this, it is a bit of a heavy thing. Okay, I'll try to do it. And then we'll have this very beautiful exercise, which is the first one we have in a very general setting. Okay, so far we have had finite things to think of. Here we have to think of an infinity of possible k-cubes, but we'll do it. And here, do that. Find a non-trivial simple graph whose automorphism group is the identity, meaning that its only automorphism, isomorphism of it to itself, is the identity, okay? I remember that the first time I gave this problem, I had a solution, and an Iranian lady had a better solution than mine. So I was very happy of this. Okay. Let's look for these 11 non-isomorphic simple graphs on 4 vertices. I have to give some examples now. I don't know why I have these spurious. Anyway, okay. Page 5. Please mind this. I now give you some examples of isomorphic graphs. So I will not have these 2 graphs in the same class because we will not count them as different because we count just isomorphism classes. Let me show what I mean. Okay. Look at these 2 graphs. At first sight, they might look very different. Still, they are isomorphic. Can we find an isomorphism here? Oh, okay, for simplicity, let me give different names here, as before. This will make things simpler. L, M, N, O, okay? And here, let's call these E, F, and G. And here, these P, Q, and R, okay? Can we find an isomorphism between these 2 graphs? A to B to C to D to E to F to G to. My suggestion, start from the edges. Any idea from outside? Any idea here in class? Please, I can't hear you.
C12.
Okay. I suggest that you start by the edges.
By the edges, okay. So E to Q, F to L, and
R?
And G to B.
G to P. And so, if I follow this, so E, we have what? We have that E has 2 ends, one with what we shall call a degree 1 and one with degree 2. So necessarily, if I take the 2 ends of the corresponding edge Q, I'm bound to give what? D must go to,
Go to O,
sure.
and
And then the other end, which is A, must go to,
A to N, and then B to L, and then
okay, B, since, so let me see, G goes to P, okay? And so when we have P, when we have G, only one of the two vertices of the two ends has degree 1, just one edge coming out of it, okay? So it must go to the one with the degree 1. So C must go to M, and B, of course, must go to L. So now we are done. Let's check what happens to F. F has A and B as ends. Its corresponding edges are, whose ends are L and then. Yes, but L and then are exactly the vertices corresponding to B and A. So our condition is satisfied, and these two graphs are isomorphic. So I will not count them as two different things, because we'll consider in just one class the isomorphic graphs, okay? So let me start. And as I said, it's not easy to do all in a small board like this, but we'll try. So we start. And my suggestion is, let's go by the number of edges, okay? And we can use what we have done at the previous stage for the next stage, okay? For finding all of them. So let's start with zero edges. And so we have just this. This is a graph, okay? Is it a graph? No, it's not a graph, because, no, it is a graph. It is not connected. We'll have a very natural adjective for that, connected, the possibility of going from any vertex to any vertex. But this is a graph, absolutely. Not everybody knows the geography of Italy, but we have two big islands, Sicily and Sardinia. Okay, so if you take the graph of the Italian railway, it is not connected, okay, in the sense that there are three pieces, all right? One for the continental part, one for Sicily, and one for Sardinia. And it is just one graph with what we shall call three components. Here we have four components, but it's not yet the time for talking about connectivity. We'll do it, okay? But now, how many graphs do we have with zero edges and four vertices? Just this, no more. So that's all with zero edges. So let's see what we can do with one edge. Also here, we do not have much imagination at work, okay? We can place it anywhere you want, okay? Where do we want it? On the left, okay. Of course, we have other graphs with one edge. Now it's time to start with the names for the vertices, okay? Of course, I could have put my only edge with ends A and D, or B and C, or C and D, or B and D, or A and D and C. No, not from A to A. No loops, no multiple edges. We are talking about simple graphs, okay? So I'm not going to consider and draw these other graphs with one edge. Why? Because they are all isomorphic to this one. Okay? So let's see what we can say about two edges. And my suggestion is that we start with what we already have. Okay? And so we already have this. Let's do like this. Okay? I'll put what I had so far, I'll put it in green. Oh. Okay, so that we can see what we do by adding something. So, madam, where do you want a further edge? Between A and C. Okay, so this is your choice. All right. Is there with the same green edge, A and B, AB, a different, meaning non-isomorphic graph with the two edges, with the green edge we have, and is there another possibility with two edges, still keeping the green edge so that we don't, we make things simpler?
From D and C.
Yeah, sure. So we have this other possibility. Do we have any other with two edges? I say no. Why? Because if you don't, now what could you do? There are not many. Let's look at the what we'll have at the very end, which is the complete graph. Okay, A, B, C, and D. Okay, so we have this, and we have tried with this, so we have this, so we have three left. Okay, if instead of these I put an edge between A and D, do I have something new? I'll do it here. Okay. But then I'll cross it because it's nothing new.
No, same isolated, one isolated vertex.
Yes. If I added this, what should I have? What would I have? Do I have something new or something which is isomorphic to one of the two drawn before?
Isomorphic with the first two edges.
Isomorphic to the first, sending A to A, B to B, but sending C to D and D to C. All right, so I cross it. This is no new one. Same thing if instead, so we had this fixed, we have tried this, we have tried this. This doesn't give anything new, but also this doesn't give anything new, or this doesn't give anything new because they are all isomorphic to this one.
Professor,
Tell
I
me.
think it's related with the degree of the vertex.
Sure.
I mean, if we only have two edges, the degree of the vertex we only can be two, so there are only two options.
No, look, we have also this possibility where we don't have any edges with degree 2. But with degree 2, actually, you, you have done everything you could. That's correct.
We only have the option of 1 degree or 2 degree if only have two edges to add.
Okay.
That's what I mean.
Yeah, sure, that's correct. And so whatever you add to this green edge, or the ones we have not yet used, you'll find something which is isomorphic to this one, okay? So with two edges, only these two isomorphism types, okay? Any graph with four vertices and two edges will be isomorphic either to this or to this, according to the behavior of degrees, as you were saying. Okay? Okay? So we are done with the two edges. Let's see what happens with the three edges. And so we'll do what? Okay, I'll do like this. And here I'll put here are the ones we had. Here are the ones we had. Now, don't forget, all possible edges are here. Okay? So now, two are already fixed, and so we can add one edge in some different ways. Okay? What are the edges we are left with? Let's see. So in this case, we are left with this, with this, this, and this. Okay? So, let's add one edge and see what happens. I would try with this one. Okay? So this is a possibility. This is a new one. And of course, like the lady would immediately do from outside, we see that we have a degree 3. And this is interesting and will help us to distinguish things. Let's see whether we have something more with a third edge to be added there. We could add, for instance, this one, this diagonal one, okay? Is it isomorphic to the one we have here? No, and it would be exactly the degree, as the lady was saying before, which helps us to understand that these two graphs are non-isomorphic. Why? Because here we have a vertex of degree 3, and here we have none. We have two of degree 1 and two of degree 2. And so they surely are not isomorphic. Okay? What happens now if we add, so, well, the one up, the one here, and we have one here. Let's see if we, What about adding this lower one? Do we get something new? Yes, and again, I would stick to the idea of the lady who was speaking from outside. Here, if I look at degrees, I can immediately see that this is something new, because here we don't have any vertex of degree 1, whereas here and here we have degree 1 vertices. So this is surely a new and non-isomorphic type, apart from the fact that we have what is called an isolated vertex, a vertex of degree 0, not present in the others. Okay? All right? And what about adding this last one, which was left out? Well, if we use it, we are already sort of starting from this, okay? And adding this one. But do we have something new if I add this one?
Is it the second one?
Exactly. It's not new because it is isomorphic to this one. Okay? All right. So the one we should have had by adding this is exactly this. And so out of this, we don't get anything new. Let's see whether we can get something new out of, out of this.
So, Professor, the thing you're trying to say, for isomorphism, the degree of vertex should be same of two diagrams, right?
This is a necessary but not sufficient condition. If you find that there are vertices of degree 2 here and no, vertices of degree 1 here and vertices and no vertices of degree 1 here, you are pretty sure that these are not isomorphic. But it's not a sufficient condition. Do you see what I mean?
Yes, I can.
Okay, so be careful. This is a useful way of finding non-isomorphic graphs, but not for finding isomorphic graphs, okay? And here, for instance, of course, we have the help of the degrees, finding that we have 2 degrees 1 and 2 degrees 2, and so we might suspect what the gentleman here has said, so that this is isomorphic to this. But for saying this, we should actually produce an isomorphism. And this isomorphism is not so difficult. I send B to D, A to B, C to A, and D to C, and we are done. We find an isomorphism, okay? So
Okay.
for finding an isomorphism, you have to produce the isomorphism. For seeing that something, that two are not isomorphic, you might use degrees. I'll come back to this important mathematical method, which is called the counterpositive in another opportunity, okay? Now let's go on with these graphs.
Okay.
Oh.
So, Professor, can we write down the key points to find the isomorphism, and for the key points of the non-isomorphism? It will be helpful for us if you write it down.
Okay. I have an empty page somewhere. Okay, I'll do it here. Tricks. Any isomorphism sense, loops to loops, sense, multiple edges to multiple edges, sense a vertex of degree k to a vertex of degree k, and there are more things, but so far we have these items already exposed. So this is, if something like this is violated, you are sure that you don't have, that what you are thinking of is not an isomorphism, okay? So if you have loops on one side, no loops on the other, they are surely non-isomorphic. If you have multiple edges on one side and no multiple edges on the other, they are not isomorphic. If you have a vertex of degree 0 on one side and no vertex of degree 0 on the other side, a vertex of degree 5 on one side, no vertex of degree 5 on the other side, you're sure that these two are not isomorphic. Is that what you were asking for?
Yeah.
Okay. So far, it's all we can see for eliminating some candidates for isomorphism. Okay, let's go back here. So this is no new. Let's see again what we have here in our. So, okay, we have this, and so we have the possibility of adding so we could add this, we could add this, we could add this, and we could add this. But what do we get? If I add this, is that new? No, because it's again like this. And if I add this, no, this I already did. If I add this, no. If I add this, no. So nothing. I do not get anything out of this no new. So with the three edges, we only have these three different non-isomorphic graphs. Okay? Let's go to 4 edges. Okay. So one is this. Again here. Things now are getting simpler because we are left with less and less possibilities. We are left with these 3 possibilities with this, okay? So we can, with this, start adding what? For instance, this. Okay? All right. Nice thing. Let's see whether we can get something different starting from this. What if we add this one? Do we get something new?
Yes.
Here we have and yes. What if I add this? Is this new? You say yes. Anybody saying no? You say no. You are not saying anything. So abstention. Okay. You're meditating? Meditate.
Yeah, I'm meditating right now.
Okay.
No.
You say
Professor, it is
no.
not.
Is it isomorphic to the other one?
Yeah.
Yeah, it is isomorphic to the other one. And I'll exhibit the isomorphism. Oh, sorry, let's again give new names here. Okay, L, M, N, O. So surely we send, so A, B, C, D, and surely we send B again. I'm sure that the lady of before has already spotted it. We have just one vertex of degree 1, and that must go to the degree 1 on the other side. So B has to go to M. Who is adjacent to B? A. So what is adjacent to M is L. So we send A to L. Okay? And then,
Exactly.
okay? And then we have two possibilities because there are two isomorphisms here. And if you look, it's exactly this. It's exactly this up to isomorphism. Okay? And so we can send C to M,
M.
D to O, or conversely, C to O and D to M. That's another possibility. So this is no new graph up to isomorphisms. Let's see whether we can get something out of the other two. Okay, we had this. Okay. And so here we can add this, or we can add this, or we can add this. So what? Well, you can see that if I add the above one, this one, I exactly get this, which we have already rejected. What if I add this one? Again, I get something which is a triangle with a tail, okay? And so again, this and this. And so if I add this last, what happens? I still, oh, let's see that. Here is something new. Okay, we don't have any, again, degrees help a lot. Here, we don't have any degree 1 and no degree 0 as well, okay? So this is surely not isomorphic to this one, okay? And it was our last possibility starting from the second graph with the 3. No, the second here. Okay, we have this last possibility. Let's see whether we get something. I already forgotten. No, it's easy. So, C and D. Okay, then what happens if I add this? Okay, nothing new, a triangle with a tail. So, no. What happens if I add this? Nothing new, triangle with a tail. What happens if I add this? Nothing new, a triangle with a tail. So, nothing out of this. So, I just get 2 new with 4 edges. Okay? And let's go to 5 edges. Okay. Okay, I can see here, no, I'll take it. So I had this with 4 edges. Okay. So my only possibilities are this or this. Okay. So let's add this. Okay. Of course, this is new because the ones before had, oh, sorry. Of course, we must have the same number of vertices and M edges. This is the first thing because we have 2 bijections. So, of course, now by adding a new edge, we get something which was not there before. Okay, so, all right with this. And what if I add the other one instead? So, the other possibility is this. And question, is this isomorphic to the other or not? Mm-hmm.
Yes, it is.
Yes.
Yes, it is.
Yes.
Good, good. Are you with me, all with me? Okay. You see that this diagonal AC is now this diagonal AD, okay? So we send B to itself, C to D and D to C, and we are done, okay? So this is no new thing, okay? Let's see whether we get something out of the other, which was this. It was like this and this and this. Okay?
Same results.
Well, we are left with this, but same result as the gentleman here has said from outside. If we add it here, we get exactly this. If we add it here, we get it flipped horizontally. So nothing new out of this. And of course, with 6 edges, there is no problem because you have the complete graph and only it. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, as foreseen by the book. And now it's high time for a break. 10 minutes break. So it is now in Italy, it's 5:47. At 5:57, I'll start again.
Excuse me, sir.
Tell me.
Would you please bring the page that you summarize the rules of isomorphism?
Yes, sure.
Thank you so much. Thank you,
But
Professor.
please remember that these are necessary conditions, okay? If you have an isomorphism, then surely you have this, okay? I want to talk about this when we start back. The counterpositive is a very important mathematical method. Anyway, this is. But remember that I'll leave all these pages on the page of the program of the course. Okay.
Uh-huh. Thank you, sir.
All right.
Professor, did you mean that all these rules should be satisfied in order the other one, I mean, the second one and the third one, be satisfied?
What I say is, if you have an isomorphism, surely this isomorphism sends a loop to a loop, multiple edges, a vertex of degree k to a vertex of degree k. If you have n vertices on one graph, you must have on the same number of vertices on the other, and the same number of edges. Necessary conditions, absolutely not sufficient conditions, as we have seen. Okay?
Okay, got it. Thank you so much.
All right. So now I'll stop. It's 5:49. Okay. I'll start at 6 p.m. Okay? 3/4 of an hour for the last part of the lecture.